Have you ever been in the middle of a really tough workout, heart absolutely pounding, sweat pouring down, and just thought to yourself, how on earth is my body doing this? How does it handle all this intense stress without just, shutting down? Well, today, we're going to pull back the curtain on your body's incredible built-in control system.
So picture it. You're out for a run. You can feel that steady rhythm of your feet hitting the ground, the cool air in your lungs. And from the outside, it looks pretty smooth, right? Just controlled, focused effort. It's a feeling we all know.
But inside, it is a completely different story. The second you pick up the pace, your internal systems just go into overdrive. I mean, look at this graph. As the intensity of your exercise climbs, your heart rate doesn't just go up, it absolutely skyrockets. It's like a controlled physiological explosion happening inside you. And that brings us to the big question, doesn't it? With your heart rate practically doubling, your body temperature climbing, your muscles screaming for more oxygen and fuel, what is stopping the whole system from just totally losing its balance and spiraling into chaos?
Well, the answer lies in this really beautiful biological principle that governs your entire internal world. It's an idea called homeostasis.
You can think of homeostasis as your body's Zen mode. It's the default state of just perfect, calm balance. When you're not stressed, when you're totally at rest, everything inside is stable, centered, and just in harmony.
Okay, so the official textbook definition is the maintenance of a constant and normal internal environment. This is your baseline. Think about your body temp holding steady right around 98.6 degrees, or your blood sugar level staying perfectly even. It's basically your body's happy place when you're just chilling on the couch.
And right here, you can see homeostasis in action. This graph shows your blood pressure when you're at rest. See how the line kind of wiggles up and down a little bit, but that average, that mean pressure line, it stays unbelievably steady. That constant, stable average, that's homeostasis. But of course, we don't spend our entire lives at rest, right? So what happens when we introduce a challenge, like that jog we were talking about? This is where our bodies have to find a new kind of normal, something called a steady state. And here's the plot twist. When you start to exercise, your body actually has to leave that comfortable, normal state of homeostasis behind. But, and this is the amazing part, it doesn't just fall into chaos. Instead, it starts working to achieve a new type of balance, one that's designed to handle the stress you're throwing at it. And we call that new balance a steady state. The key difference here is that word normal. In a steady state, a variable like your heart rate might be constant, but it's not at its normal resting level. It's an elevated but stable balance that perfectly matches the demand of your workout with your body's response.
This graph of body temperature during exercise shows it perfectly. Your temp climbs for about the first 40 minutes as you warm up, but then, look at that, it hits a plateau. It holds constant at that new, higher level. That stable plateau right there, that is the steady state. So let's just boil it down. Homeostasis, that's your body's stable, normal state when you're at rest. Steady state, that's a stable but elevated and not normal state that your body achieves during a prolonged stress, like exercise. They're both balanced, but they happen under totally different conditions. Okay, so we know our bodies can achieve these two different kinds of balance. But how? I mean, what's the actual machinery running in the background that makes all of this possible? The simplest way to get your head around it is to just think of the thermostat in your house. It gets too cold, the heat kicks on. It gets too hot, the AC starts up. Your body has a very similar, just way more sophisticated control system. It's this incredible network where your brain, your organs, your glands, they're all constantly talking to each other to maintain that balance, whether you're relaxing or pushing yourself to the absolute limit. And it really just works in 3 basic steps. Let's go back to that run. First, a sensor, like receptors in your skin and blood, detects that your body temperature is rising. Second, the control center, up in your brain, assesses this and goes, "Whoa, it's getting too hot in here." Finally, it zaps a signal to an effector, in this case, your sweat glands, which carry out the response to cool you down and get things back in balance. So why does any of this actually matter to you? Well, because this master control system is at the heart of literally everything. It's how your body produces energy, it's how you adapt to stress, and it's the very reason you get stronger and fitter over time. This isn't just some cool biology fact, it's fundamental to being alive. At the end of the day, having this incredible, responsive control system is what allows us to do so much more than just exist. It's the difference between simply surviving the stresses of the world and being able to adapt,
to grow, and to actually thrive in it.
So your body isn't just designed to stay the same. It's literally designed to find a new, stronger balance every single time you challenge it. This constant dance between homeostasis and steady state is what makes getting better possible. So the only real question left is,
How does the body actually maintain this stability? Well, its number one tool, the real workhorse of homeostasis, is a process called negative feedback. This is the system responsible for keeping you in that just right zone.
And if there's one word you gotta remember here, it's reverse. See, a negative feedback loop doesn't make a change bigger, it does the exact opposite. As soon as it senses something is off, too high or too low, it kicks in a response to push things back in the other direction, to fix the imbalance. Let's walk through this perfect example you see here. First, there's a disturbance. Let's say you start exercising, and the CO2 in your body fluid starts to rise. Okay, next up, detection. Special receptors sense this change and shoot a message to your brain. Then comes the correction. Your respiratory muscles get the signal to work harder and you start breathing faster and deeper. And finally, the resolution. You breathe out all that extra CO2 and your levels go right back to normal. The system perfectly reversed the change. It's beautiful. And this kind of thing is happening everywhere, all the time, especially with hormones. Just look at this diagram of the thyroid axis. Your brain tells your thyroid to make hormones, but if those hormone levels get a little too high, they actually send a negative feedback signal right back to the brain, basically saying, whoa, that's enough, you can slow down production now. It's this perfect self-regulating loop that makes sure you always have exactly the right amount of hormone for your metabolism. So negative feedback is all about stability, right? It's like keeping a seesaw perfectly level. But what if the body needs to do the complete opposite? What if instead of staying stable, it needs to amplify a signal and push a process towards some huge dramatic finish? Well, for that, it uses a totally different system. And that is where we meet the other type of control system, positive feedback. Now, unlike its counterpart, this one isn't about balance at all. Nope. This is about building momentum and driving a process forward to a big finale. So if the key word for negative feedback was reverse, the key word here is increase. Instead of fixing a change, a positive feedback loop grabs that initial stimulus and just makes it stronger and stronger and stronger. It's a self-reinforcing cycle, like a snowball rolling downhill, designed to create a really rapid change. And there is no better, more powerful example of this in the entire human body than childbirth. Think about it. The goal here isn't to stay stable, right? The goal is to achieve a very, very specific outcome. And this diagram shows exactly how this incredible escalating cascade works. So it starts with a stimulus. The baby's head presses on the cervix. This sends a signal all the way up to the brain, which responds by releasing the hormone oxytocin. Now here's the amazing amplification part. Oxytocin makes the uterus contract more forcefully, which pushes the baby's head even harder against the cervix. This sends an even stronger signal, which causes more oxytocin to be released, which leads to even stronger contractions. And you can see how this loop just keeps building and building in intensity, until finally, the baby is delivered. So we've got these two incredible systems, one that stabilizes and one that amplifies. But that raises a question, right? How do we know how effective a stabilizing system actually is? Is there a way to measure its power to keep that balance? Well, there is, and that measure is called gain. You can basically think of gain as a performance score for a negative feedback loop. It tells us just how good that system is at fighting off a disturbance and yanking everything back to its set point. So it's pretty simple. A system with a large gain, or a high gain, is a really powerful and effective system. And it makes perfect sense, right? The systems that control your breathing and your blood pressure have extremely large gains, because even a tiny mistake there could be really dangerous. This is why our bodies are so resilient. The high gain of these critical systems acts like a massive buffer against change. So there you have it, the constant push and pull of feedback loops, these silent engines running inside us that create both stability and massive change. From the quiet, constant corrections of negative feedback to the dramatic runaway train of positive feedback. These systems are absolutely essential to our existence. Which, of course, leads to one final, crucial question to think about. If these systems are so vital for keeping us healthy, what do you think happens when they break down?